Science and Engineering. Okay, sorry. So Professor Medar is the NEC Professor of Software Science and Engineering in the Electrical Engineering and Computer Science Department at MIT, where she leads the Network Coding and Reliable Communications Group at Research Laboratory for Electronics and serves as the Chief Scientist for Steinberg. Professor Medar's contributions to the field are extensive, and she received many awards and honors, including the 2022 IEEE Kobayashi Computers and Communications Award and 2019 Best Paper Award for IEEE Transactions on Network Science and Engineering. She currently serves as the editor-in-chief of the IEEE Transactions on Information Theory and has supervised numerous master's students, doctoral students, and postdoctoral fellows. I'm glad that we have her today as our distinguished professor. Before her talk, I would like to mention that after Professor Medar's talk, we will have technical Q&A and community development Q&A. During community development Q&A, we can have career-related or similar discussions. We will record Professor Medar's talk, and but not the community development Q&A. So please join me in welcoming Professor Medars, and thank you very much again, Professor, for presenting your work.
Thank you. Thank you very much, Fatima. Thank you to the entire group for inviting me. And I should add, I'm no longer at EIC of Transactions and Information Theory. I finished my term, and so handed over that task. So yeah, thanks a lot, everyone, for inviting me and sharing this time with me today. What I'd like to do is, I know that the interest of the group lie in items around machine learning. And what I'm going to do today is talk a little bit about how I feel that machine learning fits, or in many ways doesn't fit, with the standardization approach, and how I think standards can evolve, and I think in many ways are evolving to allow a better fit. So I hope it'll be very much a conversation. I look forward to our discussions when we have the Q&A and hearing your own opinions. So I'm going to talk about revisiting standards to allow innovation. And I think underlying this is the question of, what's the role for AI ML? And I usually use ML rather than AI. And to me, and I don't think it's only to me, ML is a means to optimize. Certainly, when I could teach our core ML course at MIT, we treat it really as an optimization course. It's a way to optimize very complicated, very large problems that don't lend themselves to, say, nice convex optimization techniques or so on, right? But it's really an optimization problem. In order to be able to be effective, your optimization needs to have something over which to optimize, right? If I tell you, okay, go ahead and optimize, but I only give you two choices, you can do really fancy optimization, but in the end, you only have one of two choices. You can only do so much with that. And I think one of the core problems right now is that the monolithic designs that have dominated, I would say, particularly in sort of mobile systems, the not just the philosophy, but the practice, go against the premise of ML. They're trying to fix everything and give you only a few choices. But then there's not much of a design space, right? If I only give you 2 or 3 choices, okay, it might be great for keeping everybody highly compatible with each other, but then what are you going to optimize over? So we need space to be able to innovate, and to me, ML is a way of basically embodying innovation. We need space of which to optimize. We still, of course, need interoperability. That's why we have standards. But I think if we revisit standards more towards allowing that interoperability and just looking, in effect, at what I'm going to call APIs. Rather than determining everything that's inside a module, then we need to reconsider those standards, but we'll have space in which to implement ML, or in effect any other kind of innovation technique. So To guide my discussion, let me tell you a little bit what I mean by this APIization and modularization. And networks is sort of there's sort of four big systems, I would call them. Um, in blue on the left, you have the systems that deal with losses, with sort of packets, frames just not getting there. In turquoise, you have the systems that deal with errors, with data being, in effect, in some way, and not just missing, but just actually altered. In purple, we have the systems that manage things like interference, the access to the medium, also deal things with like interleaving. And then at the very end, we have in light blue, what is the actual transmitter, so the actual modulation, the actual placing of the information after it's had all those processing to the left of us onto, in the case of wireless electromagnetic spectrum, and then of course the recovery and the detection. Okay, so I'm going to just talk about these four elements as being, if you will, the four the four canonical pieces that are needed to build what we're building today: losses, errors, multiple access, and then mod demod. Now, these are not separate. There's a lot of ways in which they touch and interact. But conceptually, I'm going to treat them separately, and I'm going to show that I hope, I'm going to show you or convince you that treating them separately and just letting them do their thing is a good idea. So let's start with dealing with losses. So the way we deal with losses right now is generally by repetition. I'll tell you something, somehow it doesn't get there. It may be because some errors occurred, which were not, which we were not able to recover from. We'll talk about that in the next section. And then, you retransmit. So if you were to think of this mathematically as a matrix, you would have along the horizontal lines, you would have the transmissions. And along the vertical lines, you have the data in packets. So transmission 1 on the left-hand side is packet 2, is packet 1. Transmission 2 is packet 2, and so on and so forth. Of course, if you were going to build a arbitrary type of matrix, why would you build it to look like just, a broken diagonal, which was what we have on the left-hand side? It's like just a diagonal matrix, which is a little bit broken. And of course, it gets broken because they're retransmission. So 3 gets lost and it gets retransmitted on line 7. You would build something more interesting, and that's what those other dots give you. And what those dots mean is that there's a coefficient, there's a non-zero contribution in a code from the vertical line onto that horizontal line. Okay, so transmission 2 is a linear combination in some finite field of packet 1 and packet 2, et cetera, et cetera. Okay, and then you basically are able to recover the data when you can decode, which could be that you got the data encoded or that you were able to decode. And as you can see, these are sort of very narrow matrices with just a little band around the diagonal. And so the decoding, if you think of doing the decoding as just Gauss-Jordan elimination, is very straightforward. And what you can see here is that, by the time you get to the 9th transmission, you already have on the right-hand side decoded packets all the way to 5, whereas on the left-hand side, you've only received up to packet 3. And then this acceleration, is keeps going. And eventually you just have a much better throughput, a much lower delay on the right-hand side if you look at the column that looks at the decoded packets than on the left-hand side. So on the left-hand side, you have a huge hiatus with nothing being received between 9 and 22, whereas if you go to the right-hand side, you have a bunch of receptions at 9 rather than a single one. You have a bunch of receptions that happen at 17. Okay. Now, if you're going to be doing optimization, there's some stuff that you can do on the left, but you can see there's not much because, this is a really boring matrix. On the right-hand side, now there's a ton of stuff that you can do, and you can really decide, how much of your coding do you want to be done ahead of time? How much of it do you want to be reactive? How do you want to trade off throughput for delay for in-order delivery delay, that is to say, actual decoding happening? And all of these questions now become a matter of optimization. There's not a lot to be optimized on the left-hand side. There's a huge, very rich uh, set of parameters of which to optimize on the right-hand side. And by the way, it gives you huge improvements. I was at MWC recently, if you were able to stop by the Red Hat booth, you could have seen our demo. So this is with container network interface. This is being done basically over, let's say, a Kubernetes-like system. This is with the company I co-founded, Steinwolf, the product Ramp, and you can see 100-fold improvement in the throughput. Okay, but it's not just the throughput. When you look at actually the benchmarking in terms of the jitter, you can really smooth out the jitter, so you get a 500-fold improvement in the jitter. Okay. So you can do this, of course, at higher layers, transport layers, but you can also do this somewhat in the inside the standards. And now, what I want to point out here is two things: A, how much you can optimize by having coding, which is a relaxation of the strictures of just having ARQ. But also, one of the things I want to point out here is how subtle it is to try to put it in current systems which are not allowing for it. So here, what you see on the right-hand side is a picture of how hybrid ARQ works in 5G. So in hybrid ARQ, rather than consider that if a frame was lost, it's useless, you might be able to combine multiple bad receptions of a frame to create synthetically one good reception of a frame. Not always, but you might be able to take two, frames that were not recovered and somehow decode them to give you a good frame. It's kind of a modification in effect on what I showed you at losses before. It's like a partial loss. And you can incorporate network coding, and my group is doing this along with researchers at JMA Wireless, but it's a lot of work. It works, it's good, but it really requires you to try to put a round peg in a square hole, because the system is really quite monolithic, right? And so you're having to trick it into allowing you to do good things, and of course the good things are very useful. By the way, since we're talking here a little bit about network coding, and in particular if you're interested in some of the stuff I just showed, like those matrices, I'm going to do a shameless plug coming soon on IEEE Press, Network Coding for Engineers. Everything that we've done up until now was, very mathematical, and, somewhat removed in particular from protocols and transport protocols. This book gives you, starting from scratch, assuming that you haven't even seen Galois fields, just the math you need, in a very accessible fashion, very didactic, and then lots of Python codes, lots of explanation of how to fit it into existing protocols, and along with my co-authors, Vipindev Vasudevan at MIT, Morten Peterson of Steinwolf, the company I just mentioned, and Ken Duff at Northeastern University, who's both in ECE and math. We've come up with something we really enjoy, and I hope some of you might be interested in it. Okay, so going down the stack, I would argue that we can just look at transport and just a general access unit, kind of like a GPU, but just a general unit that's doing the coding. Where again, remember, these are all matrices, so something like ARQ is just a degenerate form of coding, but something that's just going to do the encoding, decoding onto the systems. It's just going to manage the losses without the need for the kind of monolithic systems and the hybrid ARQ picture that I showed you, where we're sort of inserting ourselves to make it work well. So the next layer in our system is the one that's dealing not with losses but actually with erasures. And some of the losses, as we mentioned before, actually come from the fact that this turquoise layer that we're going to talk about, the error correction layer, has itself its own shortcomings. Now, again, talking about 5G LDPC, very few choices in what you can do in terms of coding. You have low density power check codes. They're often called modern codes. They're not modern, okay? They exist since the 1960s. I mean, of course, there's been plenty of modern work on it, but intrinsically, this is very old technology. This was Bob Gallagher, my PhD advisor. That was his PhD thesis. They're CRCA aided polar codes, so-called CA polar codes. Polar codes were developed in the late 2000s, so 2009, by Erdal Arakan, who was also a student of Bob Gallagher. So, we're talking about very few choices, and then within that, you have some choices of lengths and some choices of lengths and rates, but, not a huge number of choices, okay? And the reason why they're fixed right now, again, going back to why they're so monolithic, is because up until now, basically, you needed to have a chip that would decode that code. So if your code was CA Polar code, you would have, say, a CRC-aided successive cancellation list decoder. There are other decoders, but that would be a typical one. A random linear code has been known to be optimal since like the late 70s. I'm sorry, the late 60s, early 70s, again by Bob Gallagher, for error correction. No decoder for that. Reed-Muller code would have a majority logic. Bosch-Chaudhuri-Hockenheim code would have a Burley-Camp-Massey. CRC, so cyclic redundancy check codes, are usually only used for error detection. And what we're going to do is show you that as opposed to having to have this pile of chips, which is requiring us right now to have this really paltry choice of codes in 5G, we could instead have a single chip which uses an algorithm that Ken, my co-author, Ken Duffy and Dan just mentioned, and I have developed called guessing random additive noise decoding, which shortens felicitously to GRAND. What you see there is a picture of our first chip built with Rabia Zizicigil from Boston University. Okay, and basically the idea is, standard decoders look at why the output of a noisy channel or the noise is generally indicated by a summation. So suppose you have a binary symmetric channel, then the X would be bits and the summation would be over a Galois field of size 2. Basically, a +1 means the bit is flipped from 0 to 1 or 1 to a 0, and a 0 means that the bit is not flipped. But any noise, even a continuous noise like Gaussian noise, it always has a discrete effect. Okay, so even if the noise is not discrete, the effect is discrete because you're taking an X to some other X, okay, some other possible X. And in order to counteract effective noise, we use error correction coding, which turns a number of bits, usually denoted by little k, into a larger number of bits, generally denoted by little n. So you get n minus k redundant bits. The rate of the code is the ratio of data bits of payload over overall bits transmitted. So it's k over n. And of course, you'd like the efficiency to be as high as possible, so your R to be as big as possible, while also remaining reliable. And what capacity is actually provably the highest K over N, the highest R, for which you can still, if your N goes to infinity, make the probability of error be as small as you want, okay, after decoding. So how does GRAND work? GRAND works simply by using Y, so the output from the noisy channel, along with a codebook membership test. And it tests from most likely to least likely noise effect. It doesn't matter that they're they don't have to be, in exact order, but just, rough order of likelihood. And it inverts the noise effect. Let's call it a minus here in this line over here. It inverts the noise effect, and then it checks to see if that's in the code book or not. So at this point, the code book to us is just a hash. It just has to be a simple to compute hash. And of course, linear codes do give you a really easy to compute hash. It's called the syndrome. So that's very convenient. How well do these codes do? Well, I'll put you a little conundrum here. If you decode correctly, to what extent do I need to construct a good code? Here, let's assume that I have a binary symmetric channel with a bit flip probability of 10 to the minus 2 on the left-hand side, 10 to the minus 3 on the right-hand side. The dashed line is capacity. That's the most that you could do if the code length, which is shown here in the abscissa, was going to infinity. The ordinate is the rate r, so this k over n, it's the efficiency of the channel. The red line is a converse, so we know that we can do no better than that. And the two blue lines, the dashed blue line and the full blue line, are two theoretical bounds, never mind what they are, that are not constructive. They're just theoretical bounds to say that they should be theoretically a way to get to that rate. The target block error rate here, you can see, is also shown on the top. The target block error rate is of the order, and this is, fairly typical of the order of the underlying raw bit error rate, okay? So imagine if I had a raw bit error rate of 10 to the minus 2 and my code length was 100, then if I didn't code, my block error rate would be about 100 times 10 to the minus 2. With the coding, I get it back down to 10 to the minus 2, which is, if you will, the underlying raw bit error rate. On the right-hand side, you see 10 to the minus 3 raw bit error rate, 10 to the minus 3 block error rate. And these bounds are taken by from a nice collection of bounds curated by my colleague Yuri Polyansky at MIT. I don't show here his bound for short codes because it's actually not very good. Actually, it's in this regime that bound is only valid really in very, very high p's, like 10 to the minus 1 type p's, and those are not useful for us. They're not what you see in wireless channels. So I'm not showing, in case you're used to seeing his bounds, we're not showing them. They're worse than the converse here, so they're definitely not of use. But we've also plotted those purple dots, and since we're a small group, I'm going to ask you to guess what you think are the super wonderful codes there that are right below the red converse, and better than the best known theoretical achievability bounds. What do you think? And those are codes that we're actually getting through Grant. What do you think of those amazing codes, those purple dots? Any guesses? You can just go ahead and put it in the chat, or just scream out whatever you want. Don't worry, I'm over here. I can't, there's no judgment. Any guesses on what this might be? Any guesses at all? Okay. I'm gonna go ahead and tell you these are random linear codes, the ones that up until now had no decoder. And when I say random, I mean random. They were picked out of a hat. This created some problem for us because we were hoping that having this great universal decoder, we were going to code mine, but we weren't really able to code mine because almost all the codes were good. So in that way, with that idea, at least for the time being. Now, what happens if we have soft information? So just as background, what soft information does is it gives some idea of the likelihood that a bit is correct or not. So basically it gives some statistical information about the noise effect. The noise effect remains, of course, discrete, as I mentioned, but the statistical information can be continuous. And it gives you a way of actually ordering these noise effects. And there is an efficient way of doing this. It's called ORGRAND, order reliability bits. Uh, and last year at ISSCC, which is probably the best known CHIPS conference, we had again with the group of professors at Yazıcıcı at BU, we had a chip and a demo. And you can see that the energy per bit relative to the existing decoders, by the way, the existing decoders, some of them were CRC-ADA successive cancellation decoder. Some of them were belief propagation with recursive neural networks, et cetera, et cetera. Were all dedicated to a particular a code in general, CA Polar codes. And you can see that we did much, much better. So you see energy per bit in a log scale along the ordinate, throughput along the abscissa, also in log scale. The two little icons there that are hollow, the square and the triangle, those are actually other groups implementation of our organ algorithm, but it's not a full, it's not an actual chip, it's a synthesis. So it's just a good emulation. You can see that we can do even better than the synthesis. And the reason for that, by the way, is because and I'm hoping also to put a plug for something else I believe very much in. This was because our work, we the inventors worked very closely with Rabia and her group. And so I think that having that coordination, that collaboration with the people who are doing the theory and the development of the algorithms, with the people who are actually building the hardware. And I think the same holds very much also in ML, which I'm hoping will be of an inspiration to many of you. That really gives you a huge benefit. Okay, so there are real benefits there in that collaboration. And basically the soft information here is given as usual in terms of log likelihood ratios. So, if I'm sending, and we'll see that more when we talk about modulation, if I'm sending, say, in this case, of 4 PSK, so 4 different points, at say, 0, pi over 2, then pi, then 3.5, 3 over 2 pi, then, we can say that any symbol received that's far away from the boundary region has a high likelihood. So those are the warm areas. And any symbol that's received that's close to a boundary region between 2 different points has a low likelihood ratio. It's more uncertain. Okay, so that's what that heat map of 4 PSK in the in phase and quadrature domains, so the real and imaginary, shows you there. Okay, and so if I have hard demodulated bits, I have some soft information as to how confident I am about that bit, and that soft information is what allows me to do that reliability ordering. Okay, so does performance depend on code? Not really. Okay, not really. I mean, you can choose some bad codes. By the way, Polar codes without the CRC addition can be pretty bad. Not always, but they can be pretty bad. But we can use pretty much anything we want. We can even use polarization adjusted convolutional codes, which are Erdal Arikan's latest innovation. So those PAC codes. We can use CRCs, which, as I mentioned before, are generally used only for error detection. Here we choose CRC according to Koopman's fantastic menagerie of CRCs, CL Polo codes, random linear codes. Just as a comparison, we show here how much better we do relative to the CA-SCL, so the optimum decoder with a list size of 16. Most hardware only allows a list size of 4 or 8. 16 is very high because the complexity goes up exponentially with the size of the list. So you can see that our decoder, because it is optimum, is actually giving a big gain even for existing codes relative to what's out there right now. We're seeing about a dB gain. And basically, you can even use something like AES, which is not even supposed to be a error correcting code. You can just pad it and then use the AES, and you can see a really fantastic result in my view, which is that, you can use eCrypto as an error correcting code. So as I said, on the right-hand side, there's just one show to say that, there are some codes that are bad. You have to go out of the way. And sometimes, unfortunately, Polo codes can be bad. Okay, this is a crowd that wants to know about ML. And a question that I get often is, well, can we go off and try to optimize and make better codes? And remember that that's kind of what we were thinking at the beginning we would do. We had this optimal, universal decoder. Maybe we could go out and just code mine. And the work on the right-hand side, bottom right-hand side, is the work from Balatsuka Steaming and his collaborators. And the idea is, not really. I mean, they used a uh, you know, a an optimization package, which is, state of the art. And they used a random code. They used Orgran for both because Orgran is optimal no matter what the code. And what you can see is, you're not really getting that much of a gain. You also don't get that much of a difference in terms of the decoding time. So you can see that on the left bottom side. You can see the number of query numbers and, for the different codes. So it's not just that the block error rate's not very different. The time until you get until decoding is not very different. So I think that if there is space here for ML, it's more in actually being able to go out and figure out the length and rate of your code relative to other things that's happening in the network. So not in the construction necessarily of the code itself, but more in the design of, now that I'm no longer restricted to just, a few LDPCs and, a few CA Polo codes. Now that, the world's my oyster, what would I go off and design? By the way, if you use Gran or Orgran straight up, it only works for low to moderate n minus k. It's not the rate, it's not the length, it's the n minus k. If you want to go to longer codes like the LDPCs, you can do things such as, for instance, product codes. And there's something a little funny. I mentioned the LDPCs were from the early 60s, actually, by Bob Gallagher in his PhD. His PhD advisor was, so my PhD grandfather was Peter Elias, the late Peter Elias, who had come up, we're talking now 1950s, with product codes. So product codes, very simple constructions, like the first construction of sort of, if you will, taking a short code and trying to make it into longer codes. And you can see here is that if you use Gran as a component decoder and you use soft output, Gran actually gives you much, much better soft output than current systems using, say, Forney style systems. Forney was also a Gallagher student. Then what you can get is actually even better results than you would with LDPCs, with 5G LDPCs. Okay, so the other thing is, there's no reason to stick with 5G LDPCs for causes of, let's say, performance in terms of block error rate. We can do better. And actually, interestingly enough, what you can see here is we're comparing 5G LDPCs with 50 iterations, with us with a maximum of 20 iterations. On average, we do much, much less. And even then, we outperform. Okay, so we definitely want to give ourselves room to optimize on the erasure correction. Gran gives us room to optimize on the error correction. Again, not so much in the construction of the code necessarily, maybe, but by and large, certainly for the small or moderate n minus k codes, it's just not that much to optimize over. The theory that told us that pretty much any code is good was a correct theory. However, there may be a lot of interesting optimization. Now, how do I pick my n, my k? How do I modify them according to, how do I do my rate change, my rate adaptation? There might be some really interesting things that you can do there. And now much more dynamically, rather than just having a very small number of choices like all the generations, including 5G, have given us. So now the next step is, how do I actually manage the data with respect to putting it in the spectrum, with respect to interleaving, with respect to interference management, and so on. And I'll just give you a couple of ideas here. So interleaving actually uses up time, uses up energy, and of course increases delay. And the reason you put in interleaving is because channels are correlated. Okay, so you can see on the left upper corner before interleaving, what the bit error rate looks like, and so you interleave to make it look like like it's ID, like it's independent, identically distributed. And interleaving actually, from a theoretical point of view, is a lousy idea because the process on top left, that process, that wiggly process that has clumps, that has correlation, has a lower entropy than the process below it, right? So interleaving is mimicking higher entropy noise. Higher entropy noise would mean that actually my rate, that K over N, is lower. The rate is actually 1 minus the entropy of the noise. So by increasing the entropy of the noise, we're lowering the rate. And so what I show you here is what would happen if you used a CASCL system, like the traditional one. You need the interleaving because the block error rate versus EB over N0. EB over N0 is energy per bit over power spectral density of the noise. Energy per bit takes into account all of the energy expense, whether it be the amplification at each bit, so that's just the raw, if you will, the raw joules sent out. And it also takes into account the amount of redundancy, that N minus K that we talked about. So I could either talk to you very loudly, or I could talk to you maybe more softly, but repeating myself more often. Both of those would, both the addition of repair traffic or redundancy, or just the amplification, both of those would cost me energy. So EB over 0 takes into account both of those. And you can see that with traditional decoders, such as those that are very, very suboptimal decoders, like what we have in 5G right now, you can see that I would get to a worse performance. If instead I don't interleave, and by the way, I show you here on the left-hand side on the bottom, a traditional IEEE style decoder, matrix interleaver, you collect it as rows, you transmit it as columns. That's the way they interleave. If instead you used a grant, taking into account the correlation, the noise, you actually could do much, much better. And just to give you an idea, for the same block error rate, say 10 to the minus 3, as you would get at 3.7 dB. So like right here, instead of transmitting with a rate 1/2, as you would in a current system, you can see at the bottom right-hand corner there what kind of rate you could transmit at, and you could transmit at 90% or above. Where the abscissa here shows you rho, which is the level of correlation in the noise. Okay, in the effective noise. It might not be that the noise is correlated. It could be that you first equalize, and that gives you a colored noise from the intersimple interference. Okay. So basically, what you can see is that right now, because of the bad decoding and the monolithic codes, we're wasting about half of our resources. And so there's a lot of very fun stuff to be done there from an optimization point of view. I'm not going to talk much about the multiple access. Let me just, because I want to leave a little time for discussion, let me just go a little bit into the modulation. And the modulation, I showed you before a very simple example for PSK. You had 4 points on a circle. And it's called PSK because it's phase shift keying. You basically send information by which shift you have in the phase, which are which of those 4 points you transmit. Of course, it's all differential relative to the previous one. And it turns out the optimal modulation doesn't look like that, doesn't look at all like the modulations we currently use. It's a modulation that should be non-uniform in amplitude, non-uniform in phase, and also non-uniform in probability of use of different amplitude points. Okay, and this has been known for a long time, since I would say the early 70s by Smith, with many refinements on that since then, on Rayleigh channels by my former postdoc Ibrahim Abou Faisal, with Shlomo Shamayim and Maoz Lapidoth, and many, many, many other results since then. And I know that there is machine learning that is being currently applied to optimal modulation. I just want to say, again, this is not an area where I think applying it to the modulation itself is necessarily fantastic, because we know the optimization and we can solve it. And you can see here an optimizer and a solution. You can see 128 QAM, so quadrature amplitude modulation, just constellation, which is how we name the placing of those points on the in phase and quadrature, so in the complex plane. Transmitted by electromagnetic signals. So those 128 points just being, uniformly distributed over a grid, and all of them being equally likely to be transmitted, versus, our simple 128 point design. You can see that the SAR, which is a symbol error rate, and also the bit error rate are much better. So, and this, by the way, uses grand in the demodulation. Okay. So I think here again, maybe what's more interesting from a machine learning perspective is not trying to apply machine learning as it's been done directly on the problem, which already has an optimized solution, but more around the operation. Now that I tell you, hey, look, you have a lot more choices in your constellation, you have a bigger range over which to optimize. How are you going to optimize the operation of the system rather than optimize, again, something which already has a closed form solution? Anyway, so on that, I want to sort of repeat my message and open to discussion. So standards, I think, currently don't lend themselves naturally to machine learning. I think that modularity, so the kinds of modularity I showed you of those 4 different modules, can enable compatibility with adaptability to machine learning. So if you see here, what I mean is I have, a general access unit, a general encoding unit, general decoding unit, a general interference management unit, a general transmission unit, general receiver unit. So, it's kind of like replacing those monolithic pieces, many of which, by the way, were not designed in a very deliberate fashion, but are there very often for reasons of, in effect, historic accident and just, sedimentary layers of people just piling stuff on top of each other in committees, rather than because that's what people wanted to do. You can see, by the way, down here, the decision regions for that modulation that I showed before. So if instead you do these general units, then what you do within the general units, or how these general units are interfacing with each other in network management, there I think there's a huge amount of room for innovation and for use of ML. So my hope is that standards will move more towards APIs. I think ORAN is one step in that direction. And then they move towards that instead of having monolithic systems. And that, I think, for folks like you who are starting their career in implementing ML, will mean that you will have much more interesting, a much more interesting ground over which to explore, and over which to be able to innovate. And with that, I'll stop sharing and I'll take any questions.
Thanks, Professor Madar, for your insightful presentation. Any questions from the audience?
Feel free to pop them into chat if you prefer to do it that way. I see some old friends. Melitza, how you doing?
Muriel, I was going to write in the chat, boy, do I love it when you talk.
Oh, thank you, Melitza. It goes both ways.
I really love that you kind of speak to me. I imagine that, maybe 50% of the audience doesn't like it when you say, oh, N over K goes somewhere, and never mind where it goes. But I completely understand what you are saying. It absolutely speak to me. do have a lot of questions, and you know what they are, but I don't suppose they are very interesting for the audience. I have a couple of students who've taken Ken's class, and
Uh-huh.
they have fallen head over heels in love with Grand,
Oh,
and
very
they're
good. Very
very
good.
good. And the next thing they're going to do, and I'm sort of feeling lousy about this because they are ahead of me, and it's not a good position in life when your students are ahead of you.
Oh, they are, mine are ahead of me all the time. You get used to it. Don't worry.
Exactly. But anyways, they now want to solve all the underwater acoustic problems by using Grand. And all I told them was, go ahead. Come summer, I'll read Muriel's papers.
Well, very good. Very good.
But I am, I've always been all for random. When things get way too complicated, there's only one thing left to do, and that's the hat.
That's the hat. Absolutely. Absolutely.
So
Yeah.
I see eye to eye and with you on this one.
No, fantastic. Fantastic. No, I'm glad.
I-
Yeah, I heard about your students doing some really that they had some really interesting ideas. But yeah, I think it is great actually for underwater.
We need to, and as I was listening to you, I was actually thanking myself and saying, I gotta take a closer look at that. And, I mean, it's there, you've invented it. Why wouldn't we try it?
Why wouldn't you try it? Yeah,
I mean,
and
the previous thing
especially
that you invented worked charms for us. Just, the random packet
yeah,
coding.
yeah. I remember when we did all that fun work on it. So
All
yeah,
the
I
fun
mean,
work.
and you can see that if you use what, people often say, I can't believe that it does better than CASCL. You're like, yeah, it does.
Yeah, I
You
can't.
can
And,
see how
this
much better
difference,
here.
and that difference on the bottom right is, as far as I'm concerned, that's not a difference.
Yeah. I mean, again, it's not like you can't get anything, but it's like really, I'm not getting out of bed for that.
Exactly. And
Yeah, so-
when things are, I mean, it's also a difference between whether you're looking to improve something that's already 10 to the
Yeah.
-9,
That's
which
right.
is not my stage in life. I'm looking to improve something that's 10 to the -3rd, and yeah, I'll take
Yeah.
this.
Exactly.
So I think that, not to bore this audience anymore, you and I should get together, find the next student, and the topic is already there. The title's there.
There you go.
Okay, you in?
I'm in.
All
I'm on the
right.
record being in. We'll pull Ken in, and it'll be a party.
Exactly. Yes. Okay. Deal. Done. Next
Sounds
question.
good. Next question. Next question. Don't be shy. I haven't bitten anybody in a long time. I'm vegetarian and I'm far away, so it's very safe. Any other questions or comments even? They don't have to be technical questions.
Okay, so I have a question. I don't know.
Please.
Yeah. So what do you think about using for example, a whole machine learning operated decoder, for example, at the decoding part. So what do you think of using those things? I don't know.
Well, this one's already optimum. I mean, provably. So,
Okay.
Uh,
So
I,
for example, to reduce the complexity maybe, or reducing the latency, maybe these things.
so, some of these are one of these, I forget which one of these is machine learning based, and we're 20 times better
Oh,
in complexity.
If I may chime in, what I heard Muriel say during the talk, and I actually liked it very much, is that if there is a place for machine learning in here, it is not on the side of the coder decoder. It is on the side of finding the parameters of the code.
Yeah,
Yeah,
exactly.
yeah.
I think the parameters, I think there's lots to be done in the parameters. But, I've seen work on, doing machine learning, encoding, decoding, they rediscover Reed-Solomon or a few other things. But I mean, this is an optimal decoder, which is extremely low complexity, very low complexity, right? I mean, that was one of the reasons for making the chip, actually, because people didn't believe. They thought, oh, maybe I can do better. It's like, okay, well, you can try, but it's not going to be easy. Yeah.
Yeah.
And machine learning is often not, it's really good, as I said, at solving these very large problems where maybe the structure is not super clear.
Mhm.
Here, the structure's pretty clear. And you know what you know what you want to do. So, again, you can't never say never, but I would say it's probably not the place. Yeah. I think that definitely around the operation,
Mhm.
So rather than trying to solve things that are already solved with a fantastic solution creator like machine learning, now it's like saying, okay, now if I'm no longer restricted to just having, a handful of codes, just a few LDPCs, a few CAS, CL decoded CA Polar codes. Now what can I do? I think on the operation, on the selection of the parameters, like Melissa said, I think there's all kinds of really interesting things that you can do, and that has not been explored,
Mhm.
So that's my view. That's my
Mhm.
opinion.
Yeah. Thank you.
Yeah, no, absolutely. Good question. So yeah, sometimes I get students reaching out going, oh, I know you do decoding, I want to do machine learning decoding. I'm like, I love machine learning. I love decoding. The two together right now. Not,
Mhm.
I mean, there might be things down the road, but currently, that's not what's screaming to me,
Yeah.
It's
Yeah, that makes-
possibly down the road, but not right now. I
Mhm.
don't see that.
Yeah. Thank you very much.
Thank you. Yeah.
It's a bit over time, so maybe we can move to the next part about the
Sure.
career
And I'm sorry, I'm
development.
going to have to become a pumpkin at 2 p.m. Yeah.